Exercise 5. Here we have to work again with the binomial model. The parameters are number of trials 10 and probability of success 0.8. The success is having the highest speed internet connection. Somebody could be concerned that if these households are selected without replacement, maybe the trials are not independent because after selecting the first, there is one household fewer in the population. This concern is out of context. Since the country has millions of households, taking some as we pick the sample does not change anything in any relevant way. In this situation, we can assume that the trials are independent and we can apply the binomial model. Letter A. The probability of 7 households with high-speed internet. This is the same as we did in exercise 4. The probability of 7 successes equals 10 opportunities, choose 7 successes, times the probability of success to the power of the number of successes times the probability of failure to the power of the number of failures. This equals 0.201. Letter B. The probability of 7 or fewer households with high-speed internet. This must equal the probability of 0 households with high-speed internet plus the probability of 1 plus the probability of 2 plus the probability of 3, 4, 5, 6 plus the probability of 7 households with high-speed internet. If we were to solve this section manually, we would have to apply this formula for these 8 cases. Or we could apply the formula for 8, 9, and 10 households, add these probabilities together and subtract it from 1, using the property of the probability of the complement. But I expect you to do neither of that. What I expect you to do is put in this probability in a binomial calculator, and the binomial calculator will give you this number. This expression with the addition of these probabilities is important for showing your work. By writing this down, you are telling the evaluator, I know what must be done. I have a solid understanding of probability. Solidity and understanding is what you want to show when you are being evaluated. Essentially, you are writing here what the software is gonna do for you. I don't include here explanations on how to use one or another calculator or software. I have tutorials about that. Please watch those tutorials if you need orientation. Letter C. If we randomly pick 10 households and we know that the proportion, or probability if you prefer, of households with high-speed internet is 80%, how many can we expect to have high-speed internet among those 10? Obviously, the 80% of 10. That's to say 8. You can get this by just applying the formula. The formula says that the expected number of successes in a binomial model is the number of trials times the probability of success. The standard deviation is not so intuitive. It's the square root of the number of trials times the probability of success times the probability of failure. So in this case, 1.26. Sometimes you are expected to put these measures of center and spread in a sentence. You can say, we expect to see 8 households with high-speed internet, give or take 1.26. What we see here is the graph of the probability distribution for our previous exercise 5. As you can see, having 8 households with high-speed internet in our sample of 10 is the most likely outcome, with a probability of approximately 0.30. Having the 10 of them with high-speed internet is not very likely, with a probability of approximately 0.10. Having only 3 or 4 is very, very unlikely, and the probability of having only 2 or fewer is virtually 0. This distribution is left skewed because the probability of success is much higher than the probability of failure, so big numbers of successes are more common than small numbers of successes. The interesting thing is what happens when we increase the number of repetitions. If we have 20 trials rather than 10, the skewedness is softer. If we have 100 trials, the graph no longer looks skewed, it is now bell-shaped. It is a property of the binomial distribution that it gets closer to a normal distribution as we increase the number of trials. That's why these two distributions are usually studied together. The difference between both will always be that the binomial is discrete and the normal is continuous. This is a good moment to introduce some basic properties of continuous distributions and in particular properties of the normal distribution. The most striking fact about continuous distributions is that the probability of an individual value is always zero. Therefore, we no longer work with individual values but with intervals. Also, there is no difference between the probability of strictly less and the probability of less than or equal to, because the very equality would have probability zero. The second major point is that the probability of an interval is not obtained with a fraction, but with an integral. Now the probability is the area below the graph of what we call the density function. But you don't need to worry about this because a software will calculate these integrals for you. The most famous continuous distribution is the normal distribution. This curve is the graph of its density function, and the probabilities that we get are the areas below this curve. In Chapter 3, Part B, Measures of Position, we saw the Chebyshev's inequality. This inequality guarantees that between negative 2c score and positive 2c score, that's to say between the mean minus 2 standard deviations and the mean plus 2 standard deviations, we will have at least 75% of the distribution. This 75% is true for any possible distribution. In a normal distribution, we have much more than 75, because in a normal distribution the center is more common than the extremes. Approximately 95% of a normal distribution falls within 2 standard deviations from the mean. If we open the interval more to 3 standard deviations from the mean, we cover 99.7% of the distribution. If we close it a bit to 1 standard deviation from the mean, we cover 68% of the distribution. This is what we call the 68, 95, 99.7 rule, sometimes also known as the empirical rule. You need to know this by memory. These are the key numbers of the normal model that you must remember. Also, you must remember simple consequences of this rule. For example, in a normal distribution, what's the probability of a C-score being greater than 2? In other words, what's the probability of an individual being 2 or more standard deviations above the mean? If within 2 standard deviations we have 95%, outside we will have 5%. And because of the symmetry, half of this 5% will go to this tail in the right, and the other half will go to this tail in the left. So the probability of being here is 2.5%. Reasoning in a similar way, the probability of being above 1 standard deviation from the mean, that's to say a C-score more than 1, is 16%. In this course, we will use this notation to denote normal. What appears in the first slot is the mean, what appears in the second slot is the standard deviation. Let's practice this with exercise 6. If the middle 95% goes from 4.5 to 5.7, what's the mean? Let's make a simple diagram. We know that if we want to cover the middle 95% of the distribution, we must go from 2 standard deviations below the mean to 2 standard deviations above the mean. It is said that these marks are 4.5 and 5.7. Where is the mean? Obviously in the middle. So the mean must be 5.1. Now, what's the standard deviation? In order to cover 95%, this distance must be 2 standard deviations. Also, this distance is clearly 0.6. Therefore, the standard deviation must be 0.3. Here you have the calculations. Exercise 7. In exercise 7, we have some typical questions about normal distributions. In most of the cases, you need to use a normal calculator to answer them. Again, watch my tutorial to see how to do it with a software. Some years ago, it was common to use certain tables instead of calculators, but these tables are now falling into disuse. Letter A. What's the probability that a randomly selected woman is taller than 70 inches? This is the question in mathematical notation. In this particular case, you can answer with the empirical rule, because in a woman, 70 means 2 standard deviations above the mean. In other words, this is the probability of a C-score being greater or equal to 2. And we know, with the empirical rule, that this is approximately 2.5%. If you do the same with letter B, you will see that this is the probability of a C-score being less than or equal to negative 1.6. This is not something that you are expected to know by memory, so here you need to use the calculator. This is 0.055. To refresh your memory, I wrote here the formula of a C-score. Notice that you don't need to calculate the C-score to answer this question. I did it here for practice, to stress that these two probabilities are the same, to show that this question cannot be answered with the empirical rule, and also because in some places they want you to do so. I think they want that by inertia, because it was needed to use the tables that I mentioned before. But here you can just put the values in the calculator conveniently, and that's it. So far as the show your work goes, in a question like this, I will be satisfied if you just write down the question in mathematical notation like here. Letter C. What's the percentile of a given score? In a continuous distribution, the percentile is simply the probability of being below. In this question, what's the probability that a woman is shorter than 66.7 inches? Remember that the probabilities of shorter and shorter or equal are the same because in a continuous model the probability of the equality is 0. The calculator will tell you that this probability is 0.752. Thus, Sarah is in the 75th percentile. Quick question, how else do we call the 75th percentile? Third quartile. Remember chapter 3, part B, measures of position. Letter D. What's the probability that a randomly selected woman is taller than Sarah? Here you are asked for the complement of what we did in letter C, so this must be 1 minus 0.752 equals 0.248. Letter E. Find Sarah's C-score and interpret it. This is also from chapter 3. Value minus mean all over standard deviation. This is 0.68 and the interpretation is Sarah is 0.68 standard deviations above the mean. Letter F. What's the height of a man in the 98th percentile? Here the question is asked backwards. So you are given the probability of being below and the question is, what's the score such that the probability of a man being below is 0.98? With a calculator, you can get that this is 76.16 inches. Keep in mind that the mean and standard deviation of men are different from those of women. The last question is simply doing the same twice. For the lowest 2%, the probability of being below is 0.02, and for the top 1%, the probability of being below is 0.99. You get these scores, and then you can say, a man is eligible for that force if he is between 63.84 inches and 76.98 inches.